Hello, we're going to be doing standard 3.1, which is on the time-independent Hamiltonian and the time evolution that goes with it. We're going to be doing problem pi out of McIntyre. So a quantum mechanical system starts out in the state psi of 0 equal to c times 3 times the basis vector a1 plus 4 times the basis vector a2. And here we have the AIs, or the normalized eigenstates of the operator A, corresponding to the eigenvalues AI. In this AI basis, the Hamiltonian of the system is represented by the following matrix: H equal to E naught times 2, 1, 1, 2. And first we're going to note that the question asks, if you measure the energy of the system, what values are possible and what are the probabilities of these measurements? So, to find the possible energy measurements, we need to diagonalize the given time-independent Hamiltonian above. And the characteristic polynomial for H, once we do the arithmetic, turns out as the following. We have the characteristic polynomial here. That is equal to lambda squared minus 4 E naught times lambda plus 3 E naught squared. And then we can factor these two roots out, and we get lambda minus 3 E naught times lambda minus E naught. And by setting this polynomial equal to 0, we get our two possible eigenvalues or measurements, which are E naught and 3 E naught. And to find the corresponding eigenstates for these energy measurements, we can solve the eigenvalue-eigenvector equation. And to solve by plugging in E naught into the above equation here, we have that E naught, we have the following matrix: E naught, E naught, E naught, E naught, times the state E naught equal to the 0 vector. And we can quickly note here when we solve the system that this is a degenerate row, so we can just cancel this out. And then when we normalize the system, we get the normalized eigenstate of E naught equal to 1 over root 2 times the column vector 1, negative 1. We can do an identical process, and we get the other normalized eigenstate, which is 3 E naught equal to 1 over root 2 times the column vector 1, 1. Now that we have both of these eigenstates, we need to use the initial condition. And we're given above that the initial condition is here. And if we assume that since we're working in the AI basis, we can represent these two basis vectors using the canonical basis for R2. So A1 will be 1, 0, and A2 will be 0, 1. And also we can note that if we were to normalize psi of 0, it must be that C is equal to 1/5 above. But going through the rest of this to calculate the probabilities, I'm going to work with both C filled in as 1/5 and with C without, so we can see both going through. So now we have the following equation for the initial condition. We have psi of 0 equal to 1 over root 2 times C1 times the column vector 1, negative 1 plus C2 times the column vector 1, 1. And we can set this equal to the above state here as in matrix representation form, which is 3C, 4C as the column vector. And when we do that, we can solve that corresponding system, and this will give us the following values for the coefficients C1 and C2. We get C1 is equal to negative root 2 over 2 times C, and if we plug in C equal to 1/5 as we're given here, we have negative root 2 over 10, and similarly for C2 we get 7 times root 2 over 2 times big C, which is equal to 7 times root 2 over 10 when 1/5 is plugged in. So now that I have this, we need to quantify the time evolution for this. And here we just have psi of t is equal to C1 times e to the negative I E naught t over h bar times the state E naught plus C2 times e to the negative I 3 E naught t over h bar times the state 3 E naught. And having this, we can calculate the probabilities we desire. And to do this, we can use a result given in the book. But first we just set up our probability as usual. The probability of E naught is the modulus squared of the corresponding bra for the state and our product with our arbitrary time evolution state psi of t. And in the book it's given here that for this two-state system we're just going to get the modulus squared of C1 and correspondingly the modulus squared of C2 when we do the other one. And going through with this, we get the probability of 1/2 times capital C squared, and plugging C equal to 1/5 in, again, we get the probability as 1/50th. And similarly, for the probability of measuring 3 E naught, we have 49 over 2 times c squared, or equivalently 49 over 50. And since this adds to a total probability of 1, we know we have possibly done something correctly. All right, so now we want to calculate the expectation value of the observable A as a function of time. And since here we know that the observables A and the Hamiltonian above, we can quickly note that these don't commute, they're not commuting observables. We know that when we go through with this expectation value, we're going to get some cross terms. And this is going to represent the time evolution going through. We're going to get some oscillations in our system. So we know we can calculate the expectation value by using the following equation, which is, here we have expectation of A is equal to the bra corresponding to the state psi of t, and a product with A, and a product with the ket representing psi of t. So we can substitute in the corresponding eigenstates and matrix representations, and from there we can get our desired result. So it's a little messy, but we can set this equal to, we plug in the corresponding bra state here, and here now the coefficients we note are now the complex conjugates, so the minus signs are dropped in the exponential. And we get this here, we get this portion, and now we have our observable A, and then we just have the state above, right here. Okay, and now we can use matrix representations. And here we just have, we do a few steps involved here. So we're going to pull out an overall phase, because then we're going to get these overall phases to cancel since they're complex conjugates and their modulus is 1. And then we're going to have to take our corresponding row vectors here, and we're going to have negative 1/10 and 1/10. And then we're going to have our overall phase change here. So since we had a 3 E naught minus an E naught, we now have 2 E naught in the what's called the exponent here for our exponential. And then we have the other row vector 7/10, 7/10. And then our observable here, since we're working in the AI basis, we know that our observable can just be represented by the eigenvalues down the corresponding measurements or eigenvalues of the observable down the diagonal. So we just have the 2x2 matrix A10, 0A2, and then we do a similar process as before, but now here we just have the minuses inside, and we pull out the overall phase, and we have this phase change factor for our second part. And now if we do some more algebra and multiply through and collect a bunch of terms, we get the following expectation value in the end. So here we have A1 plus A2, which are the two possible measurements of the observable A, all over 2 plus 7/50ths times their sum again. And then we have our corresponding oscillating factor that we expected since they're not commuting observables of cosine times the cosine of 2 times E naught t all over h bar. So now that we have our expectation values and our probabilities, we have completed this problem, and that'll be it. Thank you.